Hi everyone, welcome back. Let's continue on with reactions of simple sugars. And I would actually like to split this up into two shorter videos rather than try to slog through it all at once. But as we have already verified, as we already understand, carbohydrates are simply polyhydroxyaldehydes and polyhydroxyketones. We know what hydroxy groups do, and we know what aldehydes and ketones do. And so I'm not going to be able to surprise you with any kind of new chemistry in this chapter. I think you're already at the point that I don't think anyway that we're going to run into anything truly new in these last couple chapters. So first thing to be aware of is here is one of the dehexoses in the pyranose form. We can tell that it is not glucose, right? Because this OH group is axial. I think I might have picked mannose. Everything else is equatorial, so you can double check me on that. But look at all these OH groups, including the anomeric OH, which is the hemiacetal OH. We already know that we can convert alcohols to ethers by Williamson ether synthesis. And so we can do the very same thing here. So I just picked 1-bromobutane more or less arbitrarily, but you can treat this with any alkyl halide, preferably primary. Secondary might work. And we do need to use some base. Now, this is going to be not nearly as alkaline a solution as we learned about in chapter 18 when we learned the Williamson ether synthesis. This is going to be much closer to a pH of 7. But I do anticipate that one by one, in no particular order, the OH group is going to attack the 1-bromobutane and kick off the bromide ions. And then your base is going to come in and pull off that proton and make the neutral ether functional group. Then it'll go back for another OH group, and again and again and again. So it's a similar type of mechanism involving an SN2 reaction. A variant on that is, and then I don't think you even need base, you can add a silver 1 salt, like silver 1 oxide or silver 1 nitrate. Remember that the silver 1 ion really, really loves halides, and they form exceedingly insoluble precipitates. So that will drive the equilibrium forward by removing the halide ions from the mixture. And so that's just a variant on the same thing. Either way, you wind up with an exhaustive alkylation. Again, I've just chosen this sugar arbitrarily and 1-bromobutane because it was the first primary alkyl halide that popped into my head. A similar reaction to exhaustive alkylation is exhaustive acylation. And in this case, we will treat our sugar with an excess of either an acid chloride or an acid anhydride. And again, ordinarily you will need some base, can be a mild base like triethylamine or pyridine. This, of course, does not use a silver salt because there's no halides involved. Oh, I guess there is with an alkyl halide, but remember, this is a different kind of reaction. This is not an SN2 reaction. This is a nucleophilic acyl substitution reaction. So we covered reactions of this type in chapter 21, and they're very different critters from SN2 reactions, right? They're neither SN1 nor SN2. So mopping up the halide with silver isn't really necessary here. In any case, you could treat this with, let's say, an excess of acetic anhydride, and you'll get acetate esters all around. Here I've chosen an excess of benzoyl chloride, and you will get benzoate esters all around. But whatever the corresponding acyl group is, will go in all of them. Do take note, I'm pretty sure you will actually wind up with a mixture of alpha and beta anomers, even if you started with just one of them pure over here. I think you will wind up getting a mixture of either ethers or esters over here. Because this anomeric carbon is going to have some chance to open up and go back to the aldehyde in principle before it can react with either the alkyl halide or the acyl halide or anhydride. So those are certainly possible reactions. I should mention I'm not aware of a good way of either alkylating or acylating only certain OH groups. I think OWL is crazy, and they might think that you can, but I don't believe it. I'm not aware of any way to do that successfully. Good. Let's do one other reaction. It's also possible to react only the OH at the hemiacetal, or glycosidic carbon, or anomeric carbon. There you go, 3 names for the same thing, right? Organic chemists just love it when there's multiple names for the exact same thing. Anyway, remember that OH is special in its reactivity because it can open the ring up and revert back to the aldehyde from the hemiacetal. So it's possible to react that OH exclusively and not touch any of the others by taking advantage of that reactivity, by taking advantage of the anomeric carbon being actually an aldehyde carbonyl carbon. And so what we can do is treat our sugar. This one is, again, I think that one happens to be galactose. For some reason, I know that galactose is different at carbon 4. But anyway, we're going to do the exact same reaction that we learned in chapter 19. We're going to go from a hemiacetal to a full acetal. And so ordinarily, we would treat this with some small alcohol. Methanol and ethanol are typical. You probably wouldn't want to go too much bigger than that. So generally, some small alcohol, and you'll add an acid catalyst. The mechanism that ensues, we know already, though there are actually other plausible mechanisms, but certainly this is one of them. And there may be other pathways that take place in solution, but I'm confident that at least some, if not most of the molecules, undergo this mechanism, and you'll find it is exactly what we said in chapter 19. So it's the exact same mechanism. Now, you'll notice that we are given as a final product the methoxy being down. So you'll need to look at what you're given and account for that in your mechanism. So we'll have to have our methanol here attack from the bottom face of the molecule. If the methoxy had been up, or in other words, if it had been beta, then we would have our methanol attack from the top side of the molecule. So always be sure to look at what you're given. That will give you hints about how to draw your mechanism. But there's nothing new here. We already know this mechanism. So that's a good place to stop for now. Let's leave these redox reactions and the Wohl degradation and the Kiliani-Fischer synthesis until next time, since I find those somewhat exhausting. So let's take a break here for now, and we'll see you next time to finish up the video. Have a good day.